Topic 29 is on inference for the slope of the regression line. So just as we looked at the relationship between two categorical variables using chi-squared test of independence, we want to see if there's a useful relationship between the two quantitative variables in a least squared regression line. In order to do this, we're going to test the slope. And what we want to test about the slope is that the slope is not a horizontal line, which would give us no information. It means x is not useful at predicting y at all if we have a horizontal line. So we want to test to see whether or not we have a negative relationship, a positive relationship, or we can use the two-sided test, the not equal to go ahead and see if there's just a relationship period between the two variables. So again, this is like every other hypothesis test we've done. We're going to start by stating the procedure. This is a t-test. T-test for slope of regression. And our null hypothesis is that the slope equals 0. So that's our status quo. There's no useful information given by the regression. And then our alternative is that the slope's not equal to 0, or it's greater than, or we have a positive slope or a negative relationship between the two variables. Step 2, as always, conditions. Our conditions are as follows. They're actually quite extensive for this particular test. The first one, as we've seen all along, do we have a simple random sample, or do we trust where the data was gathered from? Second, the relationship appears to be linear based on the scatter plot of residuals versus x values. We want to look at not only the regular scatter plot, we want to look at our residual plots just like we were looking at before. Usually on the AP test, they'll give you these plots, right? They don't expect to give you an extensive residual plot. So we're going to look at the scatter plot and the residual plot to determine if a linear model is a good fit, right? There's no curved relationship. There's no extreme outliers. And then the standard deviation of the response about the true line is the same everywhere. This is where, when we discussed the last time about fanning, it becomes very important. We want to check the residual plot to see if there's fanning. That means when we see fanning, we have a residual plot such as where the points are close to the line and then they get further away. The standard deviation is larger for higher x values than it is smaller. We need a consistent standard deviation throughout our model in order for us to do regression for slope. The last one, the response y varies normally about the true regression line. So typically, we're going to do a histogram of the residuals. As long as it's approximately normal or we don't see any signs that there could be a lack of normality, we're going to say this condition's met. So, do we have a simple random sample? Is the line the best model? Is the standard deviation constant? Are the residuals normal? A plot of the residuals are normal. All right. So our test statistic is calculated as follows. We're going to use the slope of the least squared regression line divided by the standard error of the slope. Standard error is something we need to be given. I'll show you how to back into it and calculate it, right? And when we do use our software, our TI-84s, to calculate this T and B, right? We can find the standard error by simply dividing the true slope of the regression line by T. So there is a way to go backwards and go ahead and get that, right? Oftentimes, the computer printouts will give us these two, and we want to calculate that standard error. So the standard error is on the formula sheet. We'll look at it in the context of our classwork, but don't worry too much about that. So on the calculator, we're going to do a LinReg t-test. We'll use the t-distribution table with n-2 degrees of freedom to get the p-value. Right? Degrees of freedom are number of observations minus 2. Remember, each observation we're recording 2 things, right? So it's just the total number of observations minus 2. So not the sum of all the numbers. And then the last part, decide whether or not we got statistical significance, right? And this is the same thing we've said for every hypothesis test throughout this year. If the p-value is less than your significance level, we reject our null hypothesis and say there's enough evidence to conclude that the slope does give us meaningful information about the relationship between the 2 variables. And our confidence interval for the slope, remember, just like every confidence interval, right? We have our best point estimate, so the slope that we get when we run our regression line. And then we have our t, determined by our degrees of freedom and our confidence level. And then we have the standard error of the statistic, in this case, our slope. So every confidence interval is about the same. Last one. So reading computer output for a least squares regression line, and I have a packet on this that we're going to go through, so we'll get much better at it. So typically, this is what Minitab, Excel will kick out something like this. Any statistical software has this, and like when we're doing regression lines, typically we're always going to be using something such as Minitab for that. So this constant, this is our y-intercept over here, this whole row. This, whatever the variable is, this is your explanatory variable. So what is the estimate for the slope of the least squared regression line? Parameter estimate right here. This is a regression analysis that I ran for the number of pages in the textbook and then the corresponding price. So the estimate for the slope of the least squared regression line, 0.147. This is the slope. This is going to be your intercept. So the regression line would look like this. Price with a hat over it equals negative 3.22 plus 0.147, and then we have our text papers. This is y-intercept in this row. This is your explanatory variable. Oh, the intercept. Gotcha. My bad. So the intercept here is negative 3.22, and that is the price of a text with 0 pages. And what's the slope? 0.147. The cost of an additional page. Right? Every increase in 1 page in the book, an extra 15 cents is added to the cost. And then the standard error. Right, so remember, our standard error, or t, equals the slope divided by the standard error of the slope. So the standard error of the slope is going to be b divided by t. We're given t over here, and we're given the slope here. So we have 0.147 divided by 7.35. Standard error of the slope, therefore, is 0.02. Right? And right here, we have point. Essentially, we just did that up here, right? And then what's the correlation? Let me finish this up. So the correlation, where typically they'll only give you r squared. So we need to do two things in order to interpret this. Use our slope. Is r going to be positive or negative? It's going to be positive because the slope is positive. Right? So to find, if I'm given r squared, I'm going to take the square root. So r squared equals 0.67. R equals the square root of 0.67. And I get R equals 0.82. Yeah. And make sure we verify that this is positive. Right. And then lastly, our 95% confidence interval. We would need one more additional piece of information. We would need to know, actually, we can use the standard error right here, 0.02. But we need one more bit of information to calculate the confidence interval, right? Because we need to know the number of observations, right? Because we need to figure out n minus 2. So in this case, right, we're going to just use 2, that plus or minus 2. And we have our slope, which was 0.147, plus or minus t star of 2 times 0.02. So I get 0.147 minus 0.04. Get 0.107. And then 0.147 plus 0.04, 0.187. If I want to interpret that, I am 95% confident that the true slope of the regression line for price versus pages is between 0.107 and 0.187. Also, to have information that says that there is a significant relationship between the slope and the regression line. So what I'm going to do is look at the computer printout and look at the p-value. So our p-value here is 0. Is this going to be less than any of our significant values? So we'd reject. For your computer printout, it's always not equal to. It's always not equal to when they're doing this. They don't do greater than or less than. There is a place you can specify on some computer software, but when you're looking at these, always assume that the alternative hypothesis is not equal to.